Hey everybody, Matt Forrest here. I'm excited to join PostGIS Day again this year. This is one of my favorite events of the year. Leaves a ton of stuff to watch after the fact. So the fact that you're here watching it live, kudos to you. And I think really appreciate you being a part of this talk. And today I'm going to talk a little bit about Apache Sedona and PostGIS, how they fit together, how they're similar in many ways. They use spatial SQL and they can look very similar if you just kind of expected them on the hood from that perspective. But I want to talk a little bit about how they fit together and how they can kind of work in unison, what they're good for, how they can, kind of build a really complete geospatial ecosystem, and how to think about that and actually do that in a short demo right at the end of this. So that's what I'm going to be talking about today. A little bit about me. I've been in geospatial my whole career. I've been using PostGIS for many years, also using a lot of other spatial SQL ecosystems and things like that. And then really, dug deep into Apache Sedona. I work at Whereabouts, so that's kind of the basis of the platform that we do. But also want to show how these pieces fit together. So that's what I want to talk to you about today. So when you look at Apache Sedona and PostGIS, you see a lot of the same things. There's spatial SQL functions. They use ST functions. There's a lot of the same things, and they're two of the best in the business when you think of geospatial tools that use spatial SQL. PostGIS has by and large the largest number of spatial SQL functions, but Apache Sedona has completely and fully committed to providing as many or as close to those as many as possible in similar spatial SQL functions as well. So that's kind of what they've been building. Now, the difference is when you look at them is, in really two areas. I try to break it apart from this perspective. When I think about PostGIS, and I've used it for many different things, to be clear, I've used it for processing over time. I've used it for, as a true database. I've used it in many different ways. So I'm really love all the things that PostGIS has to offer. But when you think about it, it is really looking at it as a database for transactional, real-time data retrieval, things like that. When I think of a database, in the most classic sense, when you boil it down to that perspective, that's what you have there. So it uses all, as you are well aware, and I'm probably preaching the choir here, it's battle tested, it's stable, it's many production systems, many of which we're hearing about today, and it's the go-to database and has been for many years for GIS, right? It provides the largest number of functions, high stability, lots of different ways to use it. But as if you've tried to push it to further limits for large scale data processing, pushing more data in, as you noted, the database, the compute and the storage is coupled, right? So those two things go hand in hand. If you need more storage, you have to add it to the database. If you need more compute, you have to add it there as well, which is why as data volume has increased, over the years, different systems have started to come out. So we've seen, systems like data warehouses, things like Snowflake, BigQuery, Amazon Redshift, those have come out, and those all use the distribution or separation of compute and storage, as well as other systems like single node services like DuckDB and SedonaDB, which is a new one from the Apache Sedona ecosystem, which I'll talk a little bit about later. But Sedona, what it is, it's a distributed spatial processing framework. So the compute and the storage are separate. You store your data in a separate location, generally in Parquet files or GeoParquet. You can read in different spatial file types from GeoJSON, shapefiles, things like that as data frames. And the compute is brought down to the storage, which means it's completely separate. You can store the data in just a cloud storage bucket, and the compute you spin up and spin down. Generally, that's done with a Spark ecosystem, although you can use Apache Flink and some other tools as well. But generally, that's how this works, is that when you spin up or have a processing task, you start your compute, it takes it and it splits it out across multiple distributed computing nodes, if you think of it that way. So instead of it being coupled, it's split up. And that's probably the biggest architectural difference here. It's not for data retrieval. You don't ask Sedona for, go find me information about this specific row or this data, or do massive inserts, updates, and deletes or stuff like that. So it's not meant for that, but it does have table-based features in the format Apache Iceberg, which is a cataloging service we'll talk a little bit about later as well. So when you think of it that way, you can think of it as an analytical engine for these massive distributed workloads. When the data gets really big or you have a massive job you need to run, we'll actually look at one of those in examples later, but that's the best way to think about these as two different systems there. Now, when I think about transactional, that's where you can do thousands of short running queries. There can be many of them running at once. So if you have thousands or tens of thousands of people accessing the same database, they can ask those questions. Postgres is meant to handle that. It's very fast. You need that, sub, millisecond latency. You need it to be get the data right now. That's what, databases are really excellent at. You have all the things from CRUD and ACID built into that. So it allows you to do a lot of different things, from APIs to tile servers to routing engines and all these different pieces. Those are like, when I think of a transactional workload, that's what I'm thinking of there. When I think of like a analytical workflow, that's a long running job that is over millions or billions of records, right? You have just a large volume of data that you wouldn't necessarily want to move into a database. You wouldn't want those same things running on the same system anyways. If you have a long running query that could, delay the transactional processing on the other side. So you kind of want to architecturally think about these as two separate systems. But of course, why I'm talking to you today is they all fit together really nicely as well. So that's what we'll be going into as well. So when I think about this, I think about spatial ETL pipelines. I want to create a pipeline that, pulls in data from maybe disparate sources, prepares it nicely, runs the analytical workload, and it can certainly pull into a transactional database to inform records in that other data system as well. On the reverse side as well, if you have transactional records that you want to pull into an analytical workflow, you can do that as well. So it provides that bi-directional component to do that. And Sedona, allows for that to connect in and kind of for these systems to really interoperably, play well together, which is going to be really important. Now, when I say like complex joins, of course, we all know and have all probably used ST intersects or contains or any of the other spatial predicate functions in PostGIS before. When we have a complex join, or maybe it's a large number of features, or maybe you need to do something at a large volume, or the geometries are highly complex, right? These are systems that you can run it very quickly on. You can integrate that with raster to vector join, doing like large distributed zonal stats, which we'll show an example of later as well. And then that batch compute that's distributed across many different clusters, right? That's a big thing. Now, one of the big scary things in all of this is the Spark backend. And if you have set that up before, how do you manage some of the different pieces there? How do you distribute or partition the data? These are all things that I think can be a little bit daunting at times. Effectively what we do at Whereabouts is try to handle that backend. So it's a service that we manage, it's serverless, and then allows you to actually distribute the data spatially, which none of the other Spark-based systems do, is that we actually have these spatial kind of predicates embedded into the partitions, which allows us to do things a lot faster than just a vanilla Spark up. So that's kind of what we do. It allows you to do that scale out processing and then, transactional scale up. So that's kind of another way to think about this on those vectors as well. So again, what are the things that PostGIS does amazing that Sedona doesn't do? Right. And it's important to call these out. I really believe that you choosing the right technology for the right role or the right, job you need to be done is really important. And these are just there's a full list, that you can kind of start to break apart. But dynamic tiling is one key thing that I wanted to call out. Doing that from, ST as MVT, creating real-time vectors at multiple zoom levels, any of the routing or network analysis, doing things like PG routing, A-star, Dijkstra, all the different routing algorithms that bring in with PG routing. Again, Sedona doesn't do that out of the box. High performance retrieval, right? If you need to, pull in very specific components of data that you can go under very fast response times. Postgres and PostGIS, are tuned to do that very fast data retrieval. And in addition, inserts, updates, adding triggers onto the database. All these things as records move in and out are really important. And Postgres and PostGIS are tuned to do this the best. And I think it's the best. And I've loved using it for all those different things. Again, database capabilities, your ACID transactions, row level, foreign data wrappers, these role-based permissions, all these built-in things. Sedona doesn't necessarily replicate that, right? Sedona is not a database, so you can't have multiple people calling it at once. It's usually kind of one, system accessing that from that perspective. One person, one request, that Spark isn't like a data system where multiple people start to grab data from it. It's really meant for one batch job and one purpose. So that's a different thing. And all the extensions, right? If you think about H3, PG routing, mobility DB, even timescale DB, all these different pieces that you can extend with Postgres and PostGIS as well is another key thing to think about. And then of course there's advanced, vector functions, there's the raster functionality, all these different things that add in and make it one of the most fully featured spatial databases that is there. That's a great way to think about it. And even into just, your, connecting PostGIS to your QGIS system, managing it as a, basically it can be your GIS server and have all these capabilities built into it. It's really incredible to do that. So whether you're, doing editing workflows, you're doing APIs, your transactional systems, you're doing production routing, tile serving, real-time lookups, all these different things are what I believe, PostGIS shines heads and tails above anything else that's out there. So that's really like, those are the things that Sedona is not going to do and doesn't do. So it's just important to keep that in mind. So what are some of the things that Sedona does that PostGIS doesn't? And that, again, picking the right tool for the job here is important. So when I talk about distributed processing, it basically takes a job, a query, whatever that might have, and allows you to distribute that over multiple compute nodes. PostGIS and Postgres is single threaded. So it allows you to say, if I have 10 workers, 20, 100, whatever, how many of that is in the backend, it allows you to process that data in parallel, parallelize the joins, dissolves, buffers, whatever you're doing there. Same thing with raster vector data, all that different stuff. It works with cloud native data like really efficiently. So you can leave that cloud native data on the bucket where it sits, be that GeoParquet, cloud optimized GeoTIFFs, things like that. It allows you to leave that data where it is and read it in as a data frame. And you can do that within that in-memory kind of data frame operation, and then write out to those formats as well. In addition, we've added support for Iceberg for geospatial file types. So it allows you to create an Iceberg catalog on top of that, which allows you to have transactional like kind of capabilities, but for an analytical workload. Again, you wouldn't want to like serve transactional capabilities, all this stuff I talked for from an Iceberg catalog. It's a catalog for analytics that allows you to reference that. So it has a lot of, built-in partitioning and a lot of things you want for snapshots of data, hens, that type of kind of, history and stuff built into it, but it's not transactional, right? That's not really what it's meant to be. It's meant to support and make these types of processing workloads a lot easier. So like I said, they look like similar things. That's why I've been using these images of like two animals and a roadrunner and a elephant. So they look very similar, but they're quite different when you think about it. And again, raster processing at scale, if you needed to do, NDVI calculations, map algebra across large areas, you can distribute and split those rasters up across space and do those calculations very efficiently there. Now, again, I also mentioned like 0 ETL cloud reads. If your data is on a bucket, be it S3, Azure, Google Cloud Storage, even on HTTP or HTTPS, you can point Sedona at the bucket and read that data in remotely, and then allows you to read that in over the wire very efficiently. With the cloud native formats, it also allows you to just pull in some of that data as needed. So if GeoParquet has built in, bounding boxes and stuff like that, if the query only requires a certain amount of data, you can do a spatial predicate push down to the file, move in what you need, and then you're processing significantly less data that you do that. And again, auto scaling Spark and serverless options that allows you to do that specifically. And then what we've done at Whereabouts is really to try to add the spatial compute all the way down to the individual node level. So you're distributing spatially, not just based off of, however Spark decides to do that. So again, these large scale ETL, cloud native pipelines, big data processing, big raster processing, raster to vector processing, spatial joins, and then into like things like ML feature engineering, GeoParquet production at scale, data, creating a, kind of this like, geospatial data lakehouse. That's really where Sedona focuses in on. That's the thing that it really wants to do and focus as a toolkit, as a standalone service. Now, SedonaDB is a new tool that we've been working on. And it's basically single node analytical power. You can kind of think of it like very similar to DuckDB. You install it with Python and effectively download it that way. But there's no backend in Spark, so you don't have to set that up. You would have to set up a Spark server to use Sedona out of the box. With this, it is a Rust-based execution engine, which is, a very specific terminology that does zero copy with arrow data access and stuff like that. It's based on Apache Data Fusion, which is kind of the Rust engine of it, and allows you to do a lot of the basics that, you can do with Apache Sedona. So it's GeoParquet in and out. It's great for laptops, even EC2 instances and memory type of things, stuff like that, even Airflow tasks and transformation. It's really focused in on spatial specifically. So doing fast things like, KNN joins, if you're doing different pieces, writing and reading GeoParquet files. It has interoperability with GeoPandas, and it can connect into PostGIS and pull in data or write data back out. So if you need that extra boost of, kind of analytical power, and when I say analytical, that's, large scale spatial joins, that's doing, area weighted interpolation queries across large, swaths of areas, things like that, even into processing tasks and those components that you don't necessarily want to bog down your transactional database with. SedonaDB provides a really nice middle ground to do that without all the, setup of a full Spark system. So that's another component of these. So like local prototyping allows you small and medium data sets, Airflow DAG tasks, even into ML feature generation at a certain speed. It's like a high speed analytical powerhouse to do those different things. So we're going to do one demo with SedonaDB. The other one, Apache Sedona, are running on Whereabouts, which gives you the full Spark BAS infrastructure. So Spark SQL, there's a data frame API, SQL API, which is where you get all the SQL functions in. Integrating with the data lake, you can kind of work with Delta Lake out of the box, Iceberg, or just Parquet files if you have a pure data lake itself. And then allows you that unified analytics across that full data ecosystem and allows you to do that in a distributed format, that horizontal scalability, which is what we want to do build in there. Now, one more I want to call out is SedonaSnow, which is where Sedona meets Snowflake. And that is basically allowing, Sedona-like functions inside of Snowflake. Now, a lot of these, so of course, Snowflake has spatial functionality that's built into it, but it extends some of that as well with, 3D functions, adding the Z coordinate, or 4D functions adding the coordinate, allows some of these different pieces there, allows some different integration and capabilities, Snowpark integration for Python and Java workflows. So there's some extra pieces that comes with if you're already inside of the Snowflake ecosystem. So it gets, kind of Sedona's engine with some of Snowflake's elasticity and some operational simplicity is what it allows you to do. So if you're already using Snowflake, if you're already using PostGIS inside of that ecosystem, how all these pieces connected, you can get some of these and that extra boost here as well if you're already inside the Snowflake ecosystem as well. So just other options about how to use Sedona within that same mix as well. Now, one piece that I wanted to talk about is Iceberg interoperability. And we just wrapped up a course over at Whereabouts talking about geospatial data engineering and using kind of the multi-hop architecture. It could also be referred to as the medallion architecture. And I've heard it referred to in many different ways, but basically it allows you to have like 3 levels of tables using Iceberg back storage that allows you to kind of create ready to use analytical data. So the whole concept is kind of using raw data inputs, be that from government files, your own data, maybe it's data from a data provider, maybe it's streaming data, it could be as PostGIS could be a source, wherever that data is coming from. You pull that into Iceberg as a raw copy. That's your first layer here, which is your raw data table. The second is where you do your silver or your processing, your heavy spatial tasks. Maybe you're doing spatial joins. Maybe you're doing conflation to things like overture maps data. Maybe you're doing, like I said, area weighted interpolation, raster to vector joins. Whatever you're doing that's heavy spatial processing, you're doing it there. And with the Spark ecosystem allows you to scale the right compute for that job. Right, so you can create different jobs that you're running, and you can choose a small instance for the small jobs. Maybe you need a heavy one for the large ones, whatever that is. But it's not all jobs running on the same compute, which is really important. And then the final step, you're creating these analytical ready tables that can go into different systems. One table might look different for a business intelligence tool. One table might look different for going and connecting into an OLAP system like a Snowflake. Table might look different going in back into PostGIS, which is what we're going to talk about today. Or it might look different going into, maybe something like a GIS tool, or maybe data outputs for an L, who knows, right? It's data going into the purpose fit in the right specific way. Now, why Iceberg? It allows you to do this and have that complete history with the tables as well. You can do appends. It has built-in partitioning. There's lots of bonuses. There's time travel, so you can go back and see the history of the tables over time. So you basically store it once, and you can, basically read and write Iceberg tables with Sedona to build that out. And then with the geometry, that's, accessing, making that even easier. That's in the V3 spec, which has been released since this summer, but it's starting to roll into some of these systems now. So basically Sedona reads it in and writes these Iceberg tables. Once it's in there, it gets all these benefits of those built-in partitions, the history, it looks like a table, things like that. So if you're writing SQL, it becomes a lot easier than using just a data frame API out of the box. It also allows you to use like table features. There's incremental processing, like I said, time travel, scheme evolution, those asset guarantees, all that stuff that you want on those tables is built right in there. And it all works on object storage. It's just data in S3 or Google Cloud Storage or Azure Blob, wherever that is. Some cheap cloud storage. And then you get into this kind of like zero ETL type of process. Like I can query that, bay it back in Sedona, be that in Trino or Spark, Dreamio, DuckDB, even into, we're adding support for SedonaDB and things like Snowflake. Snowflake allows you to read Iceberg tables. So you can immediately just say, here's this Iceberg table. You can immediately say, here's this Iceberg table I've created. I've done it efficiently and processed it, and it's ready to go. I just connect that system and it's reading directly from that table. You're not moving files or moving data back and forth. It's a very easy, like zero ETL step to connect that. So you can store your geospatial data once and then query it from any engine of your choice, including and going back into PostGIS, which we'll cover today. All right, so let's get into the demo. I've set up a PostGIS cluster here on Crunchy. It's just inside of my US West zone, so you can see some of the different data that I pulled in. I'll show you exactly how I'm doing that here. And effectively now that I have this easily spun up PostGIS database, I can start writing and reading data to it. So you can imagine if I have some data in here already, maybe there's an application, you're serving tiles from this, whatever might be in here, you can kind of see what that looks like. But let's do two different processes to actually do that. The first we're going to do in SedonaDB. Now, SedonaDB is that single node service that I mentioned before. It allows you to connect in and read in lots of different layers here. You just install it with Python, pip install. You connect it in and you allow you to do those different things. As you can see, you can just install it here. You create this connection and then you can start writing SQL and even connect to remote data sets. So that's exactly what we're going to do. Now, I've imported SedonaDB. I've established my connection. As you can see, it actually has this GeoPandas interop if your data is not in Parquet format. So I can read in this is building footprints in New York City. Just create a data frame here. And then once I have that, I can actually start to query that inside of SedonaDB. I can create that as a view here. And I'm also going to create a table here from the Overture Maps dataset. This is their places dataset. You can see I'm connecting it here to the entire dataset. And then what I'm going to do is create a query that pulls in 3 important restaurant choices inside of New York City. So pizzas, bagels, and coffee. So I'm going to pull in all 3 of those inside New York City. And then I'll create that as a memory table, which you'll see here. And then once I establish that, that's a view. So now I have my 2 data sets, my buildings and my restaurants, my pizzas, coffees, and bagels. And what I can do is create a KNN query. So the K nearest neighbors here. And basically what I want to do is find the closest, or the 6 closest of those restaurants to every building I believe this is just in Manhattan. So it's like 1.8 million buildings or something like that. So for every building, I'm going to find the closest one, and I'm going to get the average distance of those 6, right? So if you look at the query here, I have my buildings, geometries, the average distance from buildings. I use the stknn function, which is, a K nearest neighbor query kind of simplified here. And then wherever it intersects this, geometry, this WKT, which is just in the East Village. So I'm just going to pull that subset of data. So just for the demo, you can do that. You can see the values here. You can see for this building, the average distance is 101 meters or 80 meters and so on and so forth. And then basically what I do here is I'm going to pull that back into a pandas data frame, or GeoPandas in this case. And then I'm going to create my connection. Then here I create my connection back to my PostGIS database using SQL Alchemy, and I can just write that table back up. So that's what I've done so that's what I was able to do over here. Now this wasn't like a small join. This is like 1.8 million buildings to all this different data. Again, what's really nice is I can leave all the Overture Maps data over there in Parquet, pull that in, and temporary data structure here, and then run that query. And that whole query here took about like 0.4 seconds to run to do all of that. And it scales up really nicely even if you add larger amounts of data or things like that. So it's really fast once you do all the data steps there. But again, no ETL for this. The Overture data, I can leave it there. Very simple to do that from that perspective there. As you can see here, I'm over in QGIS. I have my NYC food layer here, and I can style it. And you can see these lighter areas are where they are closer to those 3 different restaurant types. And you can see there's a few key stretches here. I believe this is like, first or second, and there's Second Avenue here. And you can see these pockets where it's closer to those different assets and darker where it's a little bit further away from them. So pretty simple query and nothing too complicated there. But again, I let the analytical big join in SedonaDB, wrote it right back into PostGIS, and now I can use that and access that as a transactional table in terms of a lookup or whatever I want to do, or serve these as tiles, whatever you want to do. You can kind of do that back in PostGIS. Now, in the case of a very large join, that's what we'll do here. And I'm going to take a look at this one in Whereabouts. So I'm connected to Sedona. I've spun this up on a cluster here in Whereabouts. And what I can do here is I've actually connected to this data set called HAND, which is height above nearest drainage. So this is data that is raster data on an S3 bucket. It's open data, and it effectively allows you to see, normalizes the terrain model that gives you height along a drainage network to drive soil gravitational potentials. It's really interesting, to understand things like flash flooding and features like that, or any sort of flooding from that perspective. It's about a terabyte of raster data, so not something you're going to download or pull in, and it's global coverage here as well. So what I can do here is I've processed that data. I can read it directly as a stat catalog, read that into Iceberg with Whereabouts or Sedona, pull that in, and now I have this table which represents my raster data here. And you can see that I basically pulled it in. It's about 1.1 1.1 entry or 1.1 million entries, or I've split it into smaller tiles so it's a little bit more efficient to process. And that allows me to do it from that side, which is great. And then I pulled in every building from the Overture Maps data set here. So we've pulled that in. You could read these as data frames yourselves, but we've done the work to kind of split this into tables and buildings. So in our open data catalog, we have that as buildings. And then what I'm doing is doing a zonal stats join. I'm pulling the average value for each building or every building in Overture in a 30-meter buffer. This is just using the distance spheroid. So that's what the argument there is. And then I'm pulling the average to get that in. And false just says if I wanted to see, pixels that are only pixels that are fully contained inside the buffer. So I'm including all of them in this case, but you could turn that off. And it's just a spatial join. Instead of ST intersects, I'm using RS intersects. And you can see what this looks like here. So here's my building ID. I include the height feature, but some of those don't have them. Here's the geometry, and here's the height above nearest drainage. And then I ran that process across every single building, which is about 2.5 billion buildings across the entire globe. This is using, I think this is like a large runtime on Whereabouts. So it took about 1 hour to process for every single building that we have here. And then what I'm going to do is write a subset of that back into PostGIS. I don't want to write the whole thing. Again, this is an analytical data set. I can leave that result in Iceberg, and I can connect that into the systems that I want to strategically. I'm using a library called Wickles. A team member that I work with named Pranab. He built this out, so it allows me to actually use basically well-known locations, Wickles, for specific data using the WKT from Overture. And so what I'm passing in here is just this function that allows me to grab the well-known text for New Orleans. So I can just use this function. Now I have that WKT. And all I'm going to do is pass in, get the height, the elevation. I have to still just turn this into EWKB, so that goes into PostGIS as well-known binary. And then what I can do is basically where that intersects that bounding box or that WKT polygon. So that's what I pulled in. I just have to build my JDBC connection. And then here I write it using the overwrite feature, using my JDBC URL connection and the connection properties. And I'm going to pass it to a table called NOLA, which if I go over here, you can see now I have that table. I just have to translate that geometry from from well-known binary back into a proper geometry, which I have here. And then we can load that on the map. So here's that final map. Once again, this is processed for every building in the globe, so 2.5 billion, but all I care about is this subset here. And what we can see is that even within New Orleans, which is a relatively flat area, you have these different sort of areas. Some are a little bit higher and some are a little bit lower, but you see these different drainage areas. Even here, the central business district, but as we go along some of the different streets, you see what this looks like. And across the city, there's these light differences across these different places. But again, I can do a heavy process over here. I can pull in some of that data. Maybe it's a system for an insurance company that wants to understand, sort of elevation and risk across the city profile or anything like that. You can do these back and forth processings, connecting in PostGIS and doing it really efficiently there. So that was what I wanted to talk about today. I hope this was helpful to see how these things fit together really seamlessly and really fast and easy. I built this whole thing from starting my first PostGIS instance all the way up to finishing the process in about an hour. So it's very efficient to get started and do these different things. So I hope this helped explain and show you how you can do that. And yeah, it's been always a privilege to join this audience, and a happy PostGIS Day to everyone out there.